Okay, so I also asked a few of the students about the grading of the project. So right now the plan is um, the team members in each separate team will get the same score. But I think if we want to promote the more like active discussion or taking responsibility in the project, I think we can also add one additional term, which is the team members grade each other within the group. Okay, so now I would say the project will have three components. So one is during the presentation, right? So all the classmates graded, and then it's going to be the score coming from me, and then the score regarding your report, and then we're adding one more, which is a score from your teammates. Okay, so in this way, we want to make sure that everyone will take the responsibility in their part to work on this project. Also, more details about how this can work out. Okay. So I think now it's 10 and we can get started. So last class we talked about new topic, right? Carbon dioxide, and this class we're going to finish that up. And I realized that we were a little bit ahead of our schedule, so this class will probably be a shorter one, right? So if we do a recap, last class we introduced that the carbon dioxide is a global warming gas species, right? It also has a relatively long effect in terms of its warming potential, right? It's going to create a warming effect of 50 to 200 years. And we show this carbon dioxide concentration curve. So I didn't mention that it also has a name of the Killing curve. So Killing is a guy who started this measurement in the year of 1960s. Okay, so we can see a clear increase of the carbon dioxide concentration over this many years. So we did a simple calculation about if we assume that the atmospheric carbon dioxide concentration increased by 1.5 ppm, what does it mean in terms of the carbon emission? Okay, so now if we do a quick quiz, not about calculating this question again, but if we want to know what is the unit, the general unit in terms of the carbon emission, here I'm listing 4 units here. So what unit do we use to quantify the carbon emission per year? Okay, I'll give it 20 more seconds. Okay, we'll stop here. All right, so the correct answer should be the second one. That's gigatons. Okay. So if you just you're curious about what each unit means. Okay, so if you recall, I think in our last class we found out that the amount of the carbon emitted into the atmosphere, we're talking about carbon, not carbon dioxide. Okay, so that's going to be 3.2 multiplied by 10 to the 9th tenths. Okay, so basically that's 3.2 billion tons. And billion tons means gigatons. So we're also talking about megatons. Mega means million, right? So that's 10 to the 6th. So gigatons, that's 10 to the 9th, right? Kilo, that's 1,000. And then there's also teratons. That's 10 to the 12th. Okay, so that's why you can also find out here when we're talking about the carbon dioxide budget. right? It's using gigatons or GT. So you can also find people using a billion tons, but they're basically the same thing. Okay, so if you do a calculation, you can find out that over this 9 years, the atmospheric growth of the carbon, it's around 17. All right. So we mentioned that these carbon dioxide not only get stored in the atmosphere, they can also get stored in the ocean, right? So we know that the carbon dioxide is a acidic gas. It can form basically H2, CO3, or bicarbonate ions, right? Carbonic acid or bicarbonate ions. So once they get carbon dioxide get injected into the ocean or into the water, we're going to see this decreasing trend of the pH, which means that the water is getting more acidic, and it's going to have a significant impact on the ocean lives, right? And we mentioned that since we cannot just use the temperature to directly tell how does the climate look like, so that's why people used this. That's why people use this temperature anomaly on the global scale to tell how the temperature change over the years. And you can see that the anomaly is biased towards the positive side, which means that our Earth is indeed warming. It's just we need to collect more data points on our Earth to get this global warming effect, or this trend here. So we also mentioned that people can extract the ice core in the Antarctica, right? And then they can track out, they can find out what is the temperature many, many years ago. What is the carbon dioxide concentration many, many years ago. And you can see, as that video showed, we're in uncharted water, right? So basically the carbon dioxide concentration skyrocketed, but it seems that the temperature has not followed up yet. But if we're talking about the same trend here, we don't know what's going to happen. So here, I'm further showing the ice core data that has a little bit better resolution here. It's also plotting the methane concentration. So I mentioned methane is also a global warming gas, right? So you can see whenever the concentration peaked, you have the highest concentration of carbon dioxide and highest concentration of the methane. So whenever the concentration dropped, you also have a relatively lower concentration of the carbon dioxide and methane. So indeed, we're in, let's say, if the history is going to follow its trend, if our Earth works in that way, then we're in a pretty severe danger here. Okay. So what is the climate change is going to bring us? It's going to be the extreme weathers, right? So I think last year we had quite many hurricanes attacking the US. And it's also going to lead a lot of areas causing this drought, or let's say the countries or cities in Europe, Northern Europe. Theoretically, during the winter, it should be a lot of snow there, but they're getting melted, right? So the ice or the icebergs in Greenland, they're just being breaking up, right? Getting floated onto the ocean there. So it's causing the melting of these ice and causing a change of the regional climate or regional weather in there. So it can lead to flood and also extreme snow in some location. So now, where does this carbon dioxide come from? I think it's very simple to answer, right? That's the combustion of the fossil fuel. Okay, but if we further break it up down to different sources, so we have the coal, the carbon dioxide coming from coal, carbon dioxide coming from oil or gasoline, right? Gasoline is one type of the oil, and we have the carbon dioxide coming from the natural gas. So you can see that basically the coal and oil are occupying quite a significant fraction. So actually this also match with the basically the energy distribution, or the percentage of different energy in the United States. So this is talking about the United States. Okay. So basically the coal combustion or coal-fired power plant provides around 40% of the electricity in the US. Okay, so we're talking about let's say, reduce the consumption of the fossil fuels, or basically to reduce the carbon emission from the coal-fired power plants. But if we're talking about a fraction that's this large, 40%, we cannot do that in one day. It has to be an effort continuously, let's say for years or tens of years. Right? So gradually replace these coal-fired power plants by some cleaner energy there. So you can see that oil also provides around 40% of the total carbon emission, and the natural gas is around 20%. So basically the carbon in these fossil fuel, when they're combusted, when we extract the energy out of it, they will get converted into the carbon dioxide. And now if you look at the y-axis here, so y-axis is carbon dioxide emission, and we're using the unit of billion tons, okay? Again, gigatons here. But this is carbon dioxide. So we talked about the carbon in the beginning, right? So if we want to convert it into carbon, then you need to divide this emission number by 44 and multiply by 12, right? So basically, whenever people talk about the carbon emission or carbon dioxide emission, so the gigatons are the correct unit to use. So about the carbon emission globally, so here I'm showing the basically the carbon dioxide emission from different countries. Okay, so this is a little bit older data. That's 2006. I think China surpassed USA in terms of the carbon dioxide emission in the year of 2015. So basically, the area of these circles here represents how much carbon dioxide each country emits. Okay, so we're just listing the major countries. You can see that clearly USA and China are the major carbon dioxide emitters. Right? So we have also countries in, let's say, Japan, India, and Russia, right? So these are the, let's say, the emitters in the second team, right? So a lot of European countries, they also emit a lot of carbon dioxide. So I would say the carbon dioxide emission is not only an environmental problem, it's also a political problem. Right, so because carbon dioxide emission means fossil fuel consumption, means electricity consumption. So we cannot easily let everyone to cut these carbon dioxide emission, because without electricity, then we're probably going back to the caves, right? So this is a very complex problem, and basically we're glad to see that different countries are collaborating with each other and then try to resolve this problem. So if we list out the carbon dioxide emission for or globally as a function of time, this is starting from 1980, and you can see basically how US and China are occupying the entire emission rate of the carbon dioxide globally, right? So these two countries are occupying around 42% of the carbon dioxide emission globally. So on the y-axis, again, I want to mention the units here. So this is in million tons, okay, 10 to the 6 tons. But here you see it also has 3 zeros here. So we're still talking about gigatons here, right? So if you just put these 3 zeros in here, that would be around 20, 30 gigatons. So basically, I would say carbon dioxide emission is a very complex problem. And also in terms of its capture technologies, people are also trying to invent or come up with new techniques. But we're not talking about sulfur dioxide or NOx, because they're emitted in a smaller, relatively smaller quantity. For carbon dioxide, each carbon is converted into carbon dioxide, right? So if we talk about the total amount that we have to quantify, that's going to be humongous. And where do we store those carbon dioxide? So these are the questions that people are very interested in. And I mentioned that carbon dioxide is also sometimes a political problem, right? So last year, I think we hear a lot about the story about this girl here, Greta. Greta, right? So she basically is representing the younger generation about the the responsibility the world should take regarding the carbon dioxide emission or the global climate. And one thing we probably overlooked during these days was actually on November 3rd, it's last week, I think the election day. That is a date when the US officially left the Paris Climate Agreement. Okay, so to leave this agreement here, you have to propose. Basically, you want to leave the agreement, and there is going to be a 1-year period where all the things have to get prepared. And basically, last week, US officially left this, mainly because we proposed to leave this group a year ago. Okay, and people were joking about this action here. So they were saying 2016 Accord, this is Paris Accord, good condition, but we barely used it. Right? And we're now posting it for sale. So we don't know what's going to happen in the future. So I think likely the US is going to go back onto this climate issue here and then show the leadership in the world about how we're going to tackle this severe climate problem. And here, I'll further talk briefly about these carbon dioxide capture techniques. So if you think back on the sulfur dioxide or NOx, we mentioned that there's pre-combustion, there's in-combustion, and then post-combustion or post-combustion techniques, right? So for sulfur dioxide, you have pre-combustion and post-combustion. NOx, you have in combustion, right? The combustion modification where you change the temperature, residence time, oxygen, right? So for NOx, you also have the post-combustion. And then for carbon dioxide, since this is a new technique, people are still trying to figure out which way is the best to go to solve this problem. So that's why people presented techniques in all of these three categories. So for example, for the pre-combustion, what does that mean is we're going to first treat the coal with the oxygen here. Okay, so it's going to be a partial oxidation. We're going to extract the carbon into carbon dioxide, and the hydrogen in the coal are going to be converted into hydrogen. Okay, so we're getting more cleaner, let's say cleaner energy here, or cleaner resources or fossil fuels in terms of this energy conversion. Okay, and then further, the hydrogen basically can be sent to the power plant. Then what happens here is that carbon monoxide, people want carbon monoxide to react with water. Okay, so if you check the chemical formula, so if you go to some catalytic reaction, you can further extract the oxygen to the carbon monoxide and then convert that into hydrogen. So from this reaction here, we're also generating hydrogen. So we're basically sending hydrogen into the power plant and then combust it with oxygen and form electricity, right? And then at the same time, we're forming carbon dioxide, and then we can get it stored somewhere. So this is a pre-combustion. We're treating the coal here. But as I mentioned, there are a lot of trouble when we are trying to extract the sulfur from the coal, right? Because we mentioned that the coal particles are solid, right? It's very difficult to reach to the center of the solid to extract that amount of sulfur. And the same thing works for carbon, right? Carbon will be more difficult because this is a pure solid, and most of the component, let's say around 75% of the coal are carbon. So it's going to be a very difficult reaction, complex reaction to take place here. So this is a pre-combustion. And we also have the post-combustion method. Post-combustion means we directly still send the coal into the coal-fired power plant, right? And then the mixed gas will be carbon dioxide, water, some sulfur, right? Sulfur dioxide, NOx, and so on, okay? And then what people want to do is we'll introduce these gas species. Of course, we want to remove these acidic gases first, okay, and send it into the amine reactor here. So the carbon dioxide is going to react with amine. So amine is something that has a formula like this. Okay, so the carbon dioxide can react with this amine, and also the amine is less toxic compared to ammonia. So in this way, we can use the amine and then to capture the carbon dioxide. And also the reason why we use amine is we can regenerate amine from the reaction here. So once the carbon dioxide gets combined into this chemical formula, you can further heat it up or go through some other like low pressure or low temperature processes to regenerate the amine. So we're recycling the amine through this process while we're producing carbon dioxide. Once they're produced, we can get it stored somewhere. And then basically to further to place these amount of carbon dioxide at certain locations. So this is a post-combustion method, and we also have the in-combustion. I'll probably write it out here. So the method we use is first, when we introduce the air, we'll first use a compressor or to use a cooler to basically separate the air into nitrogen and oxygen. Okay, so we're not going to use the nitrogen in the combustion, directly burning oxygen in the coal-fired boiler here. So then at the same time, we introduce the coal particles. So we're not talking about these extraction of carbon. We still introduce the coal into the boiler here, but we're burning basically pure oxygen in the boiler here, okay? And then after the flue gas is being generated, it goes through the basically the ESP for PM removal. It removes the water, right? And then also remove the sulfur. So basically what happens here is that if we analyze the composition of the flue gas, that's going to be mainly carbon dioxide. We also already removed water, right? So that's going to be carbon dioxide and oxygen, right? Because we didn't introduce any nitrogen in here. So then if you think about this chemical reaction here, so we're basically burning the coal with pure oxygen. And we know that for any substance, if we burn it with pure oxygen, temperature will be extremely high, right? And then it's going to be difficult to manage the this combustion process. So that's why at the point here, we're going to introduce the flue gas back into the combustor here. Okay, so carbon dioxide and oxygen further back into the combustor. So in this way, the temperature will get lower down. And also it has the advantage of concentrating the carbon dioxide. So just think about this recirculation process. We're basically just recirculating the carbon dioxide until the oxygen concentration is low enough, right? And then we're going to be able to manage this flue gas. And then we can further extract the carbon dioxide and go through this combustor, go through this compressor here, and then form this carbon dioxide product. Okay, and here we're just talking about the carbon dioxide capture, right? Or let's say carbon capture. So we can capture it by pre-combustion method, we can capture it by post-combustion, or the in-combustion method. So people also talk about the, once we capture these carbon dioxide, then the problem is how do we store these carbon dioxide, right? So that's why people also call this problem as the carbon capture and storage problem, or CCS. So people also call this as carbon capture or sequestration. Okay, so basically we're talking about the same thing here. So once we collect these carbon dioxide, we need to think about ways to store it somewhere, right? And then that's also a headache for our current technologies. So in terms of the carbon dioxide sequestration, it can have both the ground sequestration or the ocean sequestration, okay? If you think about the carbon dioxide coming out of the coal-fired power plant, they're still existing in the gas phase. This is so large amount of the flue gas that we cannot store it directly in the gas form. So we have to compress it. We either compress it into the liquid form or the solid form. right? Once it's in the solid form, we also know that the solid carbon dioxide is called dry ice, right? So basically, we need to store to first compress the carbon dioxide into this liquid or solid form to save enough space, because we're not going to transport these gas species just as a gas, right? It's occupying too much of a space. So we can further store it either in the liquid form or the solid form. So for the ground sequestration, we can use liquid form and directly pump in the carbon dioxide as a liquid. And people actually already use this method for the oil extraction. Okay, so for a lot of the oil fields, let's say for extracting the oil there. So at first, the oil might be pumping itself because the pressure is so high, right? If you see, basically, let's say this is the ground, right? Say this is the oil, we drill a hole down to the ground. And then at first, the pressure here might be pretty high. So it's going to directly press the oil outside. But as we extract more oil from it, pressure gets lower and lower. We have to use some techniques to press this oil out. So what we can do is we can dig another hole and then just inject the liquid carbon dioxide into the oil field, and then basically to push these oil outside for further treatment. Okay, so people have been practicing this for a long time, but they haven't think about this as an approach for carbon dioxide sequestration. Okay, so we can use this method, similar method compared to the oil extraction. So we can also use the ocean sequestration. So basically just under the water, and then we just pump in the carbon dioxide. And since the carbon dioxide, the molecular weight is higher than water, right? So its density is going to be higher than water. So what that means is once we form the liquid or the solid carbon dioxide, it's just going to stay at the bottom of the ocean floor, right? But what this also means is that it's going to form a very dangerous zone for a lot of the animals. Let's say if the fish, they just accidentally flow into this area, then there's not going to be any oxygen here, right? They cannot live in this area. So the same problem might happen to the ground sequestration too, because let's say if there's an earthquake, if the earthquake happens, the carbon dioxide is going to get pushed out, and then we're going to form a plume of carbon dioxide. And the carbon dioxide molecular weight is heavier compared to the oxygen or nitrogen. So they're just going to float on the ground. They're never going to get diluted or vented to the atmosphere. If this plume move to, let's say, villages, right? And then that's going to cause a severe danger, high casualty there, because there's no oxygen for people to breathe. I think there was an accident associated with this carbon dioxide plume. And I think it was just a few years ago, because it's not for the carbon sequestration, actually. I think it's probably because of the oil extraction from this process. So there are a lot of difficulties for the sequestration as well. You cannot take everything for granted. Have to consider some severe scenarios when we try to find the set for the carbon storage, okay? So finally, in this class, I would like to show a video about the carbon capture and sequestration. This is from the US Department of Energy. So they spend a lot of efforts in trying to find the best technique for storing, capturing these carbon dioxide.
This video was developed by the U.S. Department of Energy's National Energy Technology Laboratory as part of a larger effort to share information about carbon sequestration, which is an important part of a portfolio of technologies that could be used to reduce greenhouse gas emissions like CO2. Greenhouses are warm because heat from sunlight passes through the glass and then gets trapped inside. Greenhouse gases in the Earth's atmosphere, like water vapor and carbon dioxide, or CO2, act much like the glass in a greenhouse. As you can see in this image, light from the sun passes through the atmosphere like it does through glass in a greenhouse. In our atmosphere, this light heats the air and the surface of the planet. Some of that heat gets radiated back out through the atmosphere, and some of it remains trapped. Life as we know it depends on this natural heat-regulating function, since it keeps our planet livable. There is concern that as levels of greenhouse gases increase, our atmosphere may trap more heat than we need. This could lead to changes in climate and weather around the planet that are commonly referred to as global climate change. Since the Industrial Revolution began, man-made CO2 emissions, mainly from the use of fossil energy, have increased significantly. Without action, these annual emissions will become even larger as population grows, and development gives millions of people around the world access to reliable energy and transportation. Without major changes, it's expected that by the year 2050, the world will go from emitting about 23 billion tons per year to emitting about 53 billion tons per year. Since CO2 and other greenhouse gases stay in the atmosphere for so long, the emissions from today will have an impact on greenhouse gas concentrations in the atmosphere long into the future. Large reductions in emissions will be needed soon to address climate change. The U.S. Department of Energy has supported a broad array of research on climate change. These technologies can be placed into three categories: energy efficiency, renewable energy, and carbon sequestration. These technologies are the three pillars of the Global Climate Change Initiative announced in February 2002. One study conducted in 2004 showed that these three technologies are key in avoiding increases in future emissions, holding them flat in the U.S. through 2050. This graph illustrates the results of that study. The top blue line shows projected U.S. CO2 emissions between 1990 and 2050. The flat brown line shows what emissions would look like if they were held flat through 2050. The gap between these two lines is equal to a reduction of 5.3 billion tons of CO2 emissions in the U.S. by 2050. That is almost as much as the United States puts in the air right now. Improvements in energy efficiency and the use of renewable energy sources, along with improvements in auto efficiency, use of alternative energy sources, and reduction in agriculture emissions, can account for nearly two-thirds of this gap, as seen in the yellow and green wedges. But even with significant investment in renewable energy and efficiency, these two technology options will not be enough to stabilize greenhouse gas emissions. Carbon sequestration is a promising technology that has the potential to significantly reduce CO2. As the light blue wedge shows, CCS has the potential to help meet the gap in emissions reductions. CCS is the term used to describe a broad group of technologies for capturing and permanently sequestering or storing CO2 in biologic materials like trees, or in deep underground geologic formations like oil fields, unminable coal seams, and deep saltwater geologic formations. The techniques used in CCS are already in use today in a process called enhanced oil recovery. In this process, CO2 is injected into an old oil field to help recover oil that would have otherwise been left behind. You probably know that plants take in CO2 from the air and store part of the carbon in leaves, stems, and in the soil. But you may not have heard of geologic storage, an approach that holds tremendous promise to store CO2 rather than being released to our atmosphere. In geologic storage, CO2 is captured from large fossil fuel users like power plants before it can enter the air. The CO2 is transported to the injection site, where it is pumped several thousand feet below the surface into layers of porous rock, such as sandstone, that are located under layers of tight, non-porous rock called caprock. The rock formations into which CO2 is injected are porous, like this sandstone. If you looked at sandstone like this under the microscope, you would see that there are spaces known as pore spaces throughout the rock. In this view, the pores have been filled with blue dye to make it easier to see them. In this view, water is being dripped onto the sandstone, and you can see it moving into the pore spaces. CO2 injected into these porous sandstone layers deep underground are contained by several layers of impermeable rock, called caprock, above the injection zone. Caprock acts as a seal preventing the CO2 from moving to the surface. This is the same kind of seal that has kept oil and gas in storage in natural reservoirs for thousands of years. As you can see here, the impermeable rock that forms a cap is very different than porous sandstone where injection takes place. The pore spaces in the impermeable rock are so small that there is very little room for CO2 to move into. As you can see in this magnified view, there is very little pore space in the caprock compared to the sandstone we saw earlier. Here we compare two magnified views of pore spaces. Both images are taken using the same magnification, and the pore spaces in both are filled with blue dye to make it easier to see them. As you can see, the water being dripped onto the impermeable rock simply pools on the surface and does not penetrate. And now look at the difference between the movement of water dripped on the two types of rock. The porous sandstone acts like a sponge as the water moves into its pores, while the water on the caprock is unable to penetrate the rock and runs off. In CCS, CO2 is present.
So based on that image, you can think about, because if water molecules cannot penetrate the rock, then carbon dioxide will not, because the size of a carbon dioxide, it has two oxygen. Oxygen is much larger compared to the hydrogen. Right? You also have a carbon, which is larger than the hydrogen atom. So if the water cannot penetrate, then carbon dioxide will not be able to penetrate.
Pressurized, so it becomes like a liquid and is then pumped into a porous rock layer. Because the well is located so deep underground, the natural pressure of the rock layers above it keep the CO2 in a semi-liquid state. Once injected, it very slowly spreads out into the pore spaces of the rock layer and dissolves into the salty water or brine, which is found in the very deep layers of rock formations. Research is underway around the world to determine how to safely and cost-effectively use CCS to address climate change. Today, there are a handful of large-scale CCS operations, and there are numerous research and development projects. In the United States, research into CCS is overseen by the Department of Energy. It consists of a core research and development program and the Infrastructure Development Initiative, which includes a network of regional carbon sequestration partnerships. These 7 partnerships represent over 300 organizations working to characterize their region's potential sequestration opportunities, research the infrastructure needed to deploy CCS technologies in North America, and validate the most promising opportunities in their regions. These partnerships will play a key role in getting CCS technologies out in the field. For more information on CCS and the DOE programs, please visit the NETL website.
Okay, so that's it for this video here. And also that's all for the class of today. And feel free to let me know if you have any questions. All right.